In this video, we'll consider the example of a quick return mechanism. First, let's talk about what they are. We saw in the four-bar analysis that for example, if we consider a crank rocker mechanism, there are extremes of this rocker, which we can find by considering that the input that linked to, which is the crank, is either overlapping or extended with the coupler. And in these positions, if you notice, these two positions, two extremes of the crank are corresponding to the two extremes of the rocker link. And we can also note that uh, each of this is 180 degrees apart in terms of the rotation angle theta. So what happens is the crank, as this link rotates, goes forward. The rocker, I mean, not the crank. As the crank rotates, the rocker goes forward, and then from this point, after it just comes back, and then it keeps rocking around these 2 points. So the time it takes to move from this position to this position versus going back to the original position, if the omega 2 is constant, that time is equal. Forward and backward strokes are equal in time. For some mechanisms, say for example in case of shaping tools or shaping machine, it requires a longer cutting stroke. This is desired. You're trying to cut a material slowly using the cutting tool, but you don't have to waste any time in coming back to the original position to start cutting, let's say, a sheet. There's a tool here, and then it has to move this direction. As it moves in this direction, it keeps cutting this, maybe a slot, a small cut, and then when it has to go back, it doesn't have to go slowly. So we want mechanisms where we can take a slow forward stroke and then come back quickly. So those such mechanisms are called quick return mechanisms. And there are a few ways in which you can develop quick return mechanisms. We will consider one example of what's called a Whitworth quick return mechanism. So here is a Whitworth quick return mechanism. It is essentially comprising of one inversion of slider crank, where the slider is on this uh, rotating link, and then this is extended on the other side, and another slider crank is added to that. That uh, does the forward and the reverse strokes that we were just now talking about. So we have certain, so for this example, we will consider the dimensions of links as follows. And the omega value for the crank is 2.5 radians per second. And for this example, we'll also consider alpha 2 to be present. We'll say this is 20 radians per second square. So at this instant, we want to determine acceleration of the slider S. And we want to determine the angular acceleration of AR and angular acceleration of RS. So whatever is the angular acceleration of AR is same as angular acceleration of the AB portion. So we're interested in finding those. Note that when I mentioned alpha 2 is 20 radians per second, it is at this instant that we are considering alpha will be 20 radians per second. And we are trying to find the remaining quantities when the omega for this system, omega 2 for this system, has become 2.5 radians per second. Obviously, the next moment, if I change, if I move forward in time, if I do time stepping, at that point the omega is not going to remain 2.5 anymore because alpha 2 is present. So we are trying to solve this for the situation when alpha 2, given alpha 2 is 20 radians per second square, omega 2 at this instant is 2.5 radians per second. So first in this, we will try to draw the velocity diagram. So we can start here. We know P on the slider has velocity which is going in this direction, which is orthogonal to OP. From there, we can say that the velocity of the point Q, which is on AB, has to be orthogonal to the AB link, which is going. So this has to be, this is completely known. This is V of point P, which is on the slider block. The point P on the slider block is also a point on OP, and OP is rotating at omega 2. So we know VP magnitude will be equal to link OP, which is 240 millimeters, times omega is given as 2.5 radians per second. So this becomes 480 plus 12600 millimeters per second. So that's the velocity of point P with respect to O. So you would consider this length and you will equate that to 600 millimeters per second. So that becomes your scale. Next, we consider that the velocity of point Q on AB, we can talk about that with respect to point A, which is pivoted, it's at ground. So we can draw that perpendicular line. We don't know what that is, but we understand that the component of VP, which is orthogonal at to AB, that is the transmission part of the velocity, is going to uh, result in the velocity of the point Q on AB. So we can drop a perpendicular like this to split the VP into V slip and V transmission. So that way we find out this should be velocity of point Q. So we can find this as velocity of Q, and then we can say this is velocity of the point P with respect to Q at this instant. So we can also find the slip velocity like that. So this is velocity of point P with respect to Q. Then we can then consider that R with respect to A is on the other side. So as the, say, if I consider this is pivot, this is a link passing through this. If this is going this way, this will go in this way. So in the same manner, we can consider the lengths of AR and AQ, which are given AR and AQ, or well, this is known. This length is known. This is for AQ, and we know this quantity. So correspondingly, we can draw on the other side for AR. With that, we know from here with respect to, so this is V of R. From here, we know V of S should have some, S with respect to R will be this way. And then there will be V of S, which is going to be horizontal. So these two intersect here. So this point becomes velocity of the slider. This is V of S, and this is V of S with respect to R. So that was kind of straightforward. We have seen all of these elements before. We just have to apply it more than once. Then from here we can move on to, okay, so from this part, now we have omega of this body, AR. For instance, if we consider this, we know this is of certain length, let's say R. and then we can connect that. And let's say this is some length p. If p is 600 millimeters per second, then r equals what? So we can answer this question. We can just simply say that this is equal to 600 divided by p times r. That's millimeters per second value of what is the velocity v of r. So once we get this as v of r, we can then divide that. So omega of the AR should be equal to V of R magnitude divided by AR. AR we know is 165 millimeters. So from there we can find out what is the omega of AR. Similarly, we have V of SR. We know what is the magnitude of this. We can, using this scale, we can find out what is the magnitude of ESR, and then we can divide that by the link RS to get omega of RS. So these were the unknowns. We have found these. We can additionally find out what is the slip velocity VPQ, and then use these in the acceleration analysis, because now VPQ will show up in the Coriolis component. So we can now do the acceleration analysis. Before we get to the acceleration diagram, let's point out something with respect to the slider. The slider is on a rotating link, and so there is going to be slip acceleration and Coriolis acceleration. So we have VQ with respect to P going in a certain direction as the link OP rotates, and for the Coriolis acceleration, we will turn this vector by 90 degrees in the direction of the omega of link AB, which we would have identified through the velocity analysis. So this will become acceleration Coriolis of Q with respect to P. So this we need to keep in mind. We also know that the slip acceleration is going to be perpendicular to this. So now we can get to the acceleration diagram. Let's start here. This is the angular acceleration of point P normal, and there is alpha going clockwise, so we can draw this is tangential acceleration of point P, and from here we also know that there is a Coriolis component, so we can draw that. Maybe just till here, and then we know that there is a slip. There is acceleration of slip along this line. On the other hand, we can look at Q from A and say that there is a normal acceleration of this point Q, and then there should be a orthogonal to this, there should be a tangential acceleration of Q. So it will intersect, and we will know now from this what is the acceleration of Q tangential, as well as what is the acceleration of slip of Q with respect to P. So this becomes AQ with respect to P. This is slip, and this is the tangential acceleration of point Q. So in effect, we find that this is acceleration of Q, and we can extend that acceleration of Q to the other side based on the length of point from A to Q versus A to R, and that gives us this point, the acceleration of point R. From here, we know that the um, normal acceleration of point S with respect to R is like this. This is A of S with respect to R normal, and then orthogonal to that, we can get the tangential of the same. We also know that the acceleration of S has to be on the x-axis of this diagram, so we can extend that over there, and this intersection point becomes the point S. We can get acceleration of point S, and we can get acceleration of S with respect to R tangential, and this. So from here, if we read this length and then convert it to this right using the right scale, we get the acceleration of S uh, in millimeters per second square. So we can get the alpha of AR, which is same as alpha of AQ. We can get that from acceleration tangential of the point Q with respect to A divided by AQ. And then similarly for RS, we can get uh, tangential of S with respect to R, and then divide that by RS. So those will give us the complete solution.